Welcome everybody. We're just going to wait for a couple of minutes for everybody else to join. Okay, now first of all, thank you very much for your time. I do appreciate that everybody's busy and good morning or good afternoon wherever you are in the world. My name is Wasim here, who will be doing the main presentation. And I've got my colleague David here, who will be basically helping with the Q&A and also any questions, any queries you may have regarding the presentation, if you're having any issues. So what I recommend is that if you have any issues regarding the presentations or audio, please type the question in the chat box. And if you have any question regarding the presentation software, type your questions in the questions panel. And my colleague David here will basically try to answer them as we go to the presentation. And if towards the end of the session, we can go through them together. Now, the idea is we have an hour here, so probably take us 35 minutes or so going through the presentation. And then we'll have ample opportunity to go through Q&A afterwards. This session is recorded, so which will be shared after the webinar. Everybody who has registered and who has attended will receive a recording of the webinar. So we're just going to switch off the cameras so that the screen is a lot bigger rather than a smaller screen. So we're just going to switch my camera off and we'll begin. Okay, so welcome again. So the idea here today is to talk about large assemblies within simulation using software called Altair SimSolid. And before we begin, just as a brief intro about myself, I've been working with Symetri for over 10 years. I have experience with various simulation tools, including MSC, ANSYS, Algo, and obviously the Autodesk portfolio. And some of you might be familiar with, if I've trained you on Nastran, I've also authored the Nastran books based around Inventor and Nastran. So enough about me. The agenda basically is to go through comprising traditional solutions against SimSolid, because I think everybody here is more or less familiar with the various traditional softwares like ANSYS, Inventor, or Nastran. Then I'm going to go through the SimSolid demonstrations, showing you some various examples which I believe are large and complex to do inside Nastran, for example. And then I get a question asked lots of times, if it doesn't, how are the results? How good are they? How can you compare them? So I'm going to go through some documentation to show you the results accuracy from SimSolid. Also in the panel, there is a handout section. There are two PDF documents which I suggest you can download. One is regarding how SimSolid technology works, because you'll notice when I go through the presentation, SimSolid is one of the softwares in the world which does not require any meshing. So how does it work? So the technology overview web paper will explain all that. And then there's a big, thick manual on examples based on hand calculations or theoretical examples of how we have compared SimSolid. So this is a document from Altair which you can download as well. Okay, so let's begin. So one of the tasks which we are basically spend a lot of time in is geometry simplification, and that could basically mean simple removal of features, whether it's holes or radiuses. Or it could be geometry replacement with something simpler. It could be a surface, it could be a beam or a bar, or we have to then spend maybe a significant amount of time trying to fill the gaps or remove the gaps. So depending on the complexity or the scale of your geometry, it could take from minutes to hours. Now, obviously, when we're doing large scale examples, it could mean a lot of time. In some cases, it could take us days. Now, one of the advantages of SimSolid is, when you'll see that in a moment, that we don't require any simplification whatsoever. It works directly on your CAD geometry, and it doesn't care about gaps and overlaps, which you'll see in a moment. Now, the other main task inside traditional software like Nastran, ANSYS, or any other tools is that we can spend a fair amount on time on meshing. If the geometry is not perfect, then we'll have meshing errors. We also then have to check whether the mesh is good or bad. Things like aspect ratios. This is an option. You don't have to do it, but some people prefer to do it. And then we have to run it 3 or 4 times to understand whether the results have been affected by the change in mesh. And what we refer this to is solution convergence. So we have to run it once, twice, and then 3 times to get an idea about if the results I can believe in. On the other hand, SimSolid does this all automatically. It does not require a mesh. The meshing is irrelevant. It does an automatic convergence, so you don't have to do anything. The only thing you do is to bring the geometry in, apply the loads, the constraints, and then press run. And it takes not a lot of time, and it's very fast, as you will see in a moment. Right, let's take a simple example. Some of you may be familiar with this. From our training example, we have a simple example here. We then go through a convergence process. So you see the results are different as the mesh gets smaller and smaller. And this demonstrates that we are going through 4 different analyses, 4 different solutions to decide whether we are happy with the final result of 87.65. Now, this is a very high level overview of how SimSolid works. Now, it basically doesn't require a mesh. It goes through some sort of error convergence process in the background. And if you really want to know how it works, then you can download the handout from the it's called SimSolid Technology Overview white paper, and it'll give you a lot more detail of how it does it. So in brief, what it basically means is that you don't do anything. The only thing you do here is change to adapt for stress, and then it just runs a couple of seconds compared to several minutes on this simple example. Now think about this. If that's minutes to seconds, how fast do you think it will be when we do large-scale models? Because large-scale models inside Nastran and Inventor can take a long time to set up and run. So this shows you a very simple overview of what is happening. Now, the other reason of large-scale examples is there are 2 areas which are of interest: welds and bolted connections. Now, so let's have a look at the weld and how Altair Simulation handles these at the moment. Now, let's take this bridge example, for example. Now, if we use solid elements, which is one of the options by default, then typically as engineers, we need to model the weld as a geometry or fill the gaps in. So we do it as either a fillet or a chamfer. So you have to physically model the weld. Now, if you then decide to use mid-surface extractions to make the analysis go faster, then you end with a shape like this, which you can see there's a gap between the 2 plates, which means we cannot create welds. And then the other option is that you model the whole thing again as a surface model, and then you can model the surfaces as surfaces if you wish to do so. Or the third option for a large structure like this is beam elements, which also does not account for welds. So the only option is solid elements and model the weld geometry, or surface geometry with a combination of solid welds, which all requires time and effort. Okay, so what you see here is the example here. On the left-hand side here, we see the box sections, and then inside SimSolid, which I'll show you later, is that you can see how simple and how easy it is to create the welds. Okay, so that's the weld demonstration, and we'll go through the presentations. Now let's have a look at bolted connections. Now, inside Inventor, for example, we can analyze the bolted connections as they are, but we cannot apply a preload, and we would have to create and modify the contacts from bonder to separation, which can take a lot of time, especially when you have lots of bolted connections. In Nastran, we cannot use the bolts with a preload, so we suppress all the bolted connections, and we simply then create a special bolted connection in Nastran. If you are familiar with Nastran, then you'll understand what I'm saying. But yes, you can use the bolted connections, again, like Inventor, but you cannot apply the preload. And a lot of customers and colleagues I've spoken to want to be able to apply a preload or a torque to make it more realistic. So one of the options is, in a classical method, whether using ANSYS or other products, you can suppress the bolted connections. Then you would have to split the faces to represent the diameter of the washers, and then you can go and define your bolted connections. And this can be a very tedious task if you have several hundred bolted connections. Inside SimSolid, the software automatically detects what a bolt is by the shape and size of it. It will then automatically create bonder contacts and sliding contacts as how bolts behave, and it does it automatically. You don't have to do anything. Okay, so in brief, I know everybody here has got tools they're already using. In brief, SimSolid is ideal for complex models which will be almost impossible to mesh using traditional tools. They could be either 3D printed parts, they could be either additive manufactured, lattice structures, or organic structures. And also it's ideal for large structural framework models and welded fabrications, which are not so easy to do inside traditional softwares because you have to represent it with very simple primitive geometry like beams and surfaces. And finally, one of the biggest strengths of SimSolid basically is it works on original geometries, and it's very, very fast. Okay, now let's see the software in action. So you see here I have 3 different examples with 3 different complexities, and I'm going to show you for the next 20 minutes or so how SimSolid handles structures like these with ease. Okay, let's have a look. Okay, so what we have here is a very detailed platform, which is basically taken from Inventor as a step file. So you can see here we have bolted connections, we have the washers, we have everything in here, and we also even have this platform here, which is a very thin shape. Just to give you an idea how big this model is, we can go into the assembly here and have a look. So we have almost 700 components of about 138 nuts and bolts. So it's a pretty detailed geometry, guys. Okay, so how do you analyze this? Well, typically what you would have to do in a traditional software is to remove the handrails and the ladder and simply concentrate on the platform, and you may even need to remove the mesh at the top because that is a big task to mesh. So what I'm going to show you here is that we'll do a simple modal analysis and to see how fast it runs with the geometry as it is. So the first thing we would do here, once the geometry comes into SimSolid, we assign the material. So we go into here. So that's the only thing which will be different from your Inventor or Nastran models. You would have to go and define your properties here. So pick steel, apply that to everything. And the next task here, you can see here now, if I expand that, you can see steel's been assigned to everything. So the next task we're going to do here is we're going to create connections. So everything is an assembly. So how do we go and create connections? So I'm going to go and use right here. It comes with a default setting of 1 and 1. I'm simply going to keep the default settings and I'm going to press the button and see if it connects everything. Okay. So I'm going to press OK and see what it hasn't connected. So it looks okay, but when I start looking at, okay, I can't see what that is. So I'm going to pick the magnifying glass here. Oh, it's the cap at the end of the pipes or the handrails. Let's do the next one. It's okay. So these don't seem to be important for my analysis. And then we have this between the handrails. So I could either do 2 things. I can either make the tolerance bigger, or I'm going to simply suppress them. I don't think these are important, so we'll suppress them. You can delete them, but I want to suppress them because you may decide to include them afterwards. So I'm going to suppress these. I'm going to press close here and just do a final check. I'm going to see if anything is not connected. Okay, so far so good. The next task is when you have large scale models, what Inventor, Nastran or SimSolid do, if one part is connected to another part, then it will say it's connected, but it will not say if it's fully connected. So for example, the tube, let's take this tube here, it might be connected there, but it may not be connected here. The best way to find out if components are still not connected for large scale models is to do a modal analysis, because if I look at my connections, if I go to regular connections and fasten connections. Can you see how many connections I've got? I don't think anybody's got the time to go and check every single contact there. We have thousands and thousands of connections. So the best way to do this, even with Nastran, anything else, is to do a modal analysis. So I'm going to go and click on modal analysis here, and let's say we run 20 more to see if anything is disconnected. So if I press OK, the only thing I need to do here for the modal analysis here is I'm going to fix it at the bottom here. So let's do this one. Let's fix that one. 2, 2, 3, 4, 5, and 6. Okay, so let's have a look now. So I think we're ready. Now remember, this model here is pretty large and detailed, and what happens is for automatic convergence, if I show you there, look, this runs through 3 iterations automatically. How do I know that? If I make that custom, you can see it runs for 3. If you want more accurate results, if you're interested in stress, then you can go for stress, which is 4 iterations. So I'm simply going to look at displacements, and I go to 3 different solves. If I press OK, I'm going to press run, and you'll see how fast it is compared to something like this if you were to do it inside Inventor or even Nastran. So we haven't done any simplification whatsoever. We just brought in the geometry as it is, applied some constraints, created some contacts, and it is running through 3 iterations. So it's running 3 times at least. So that's the first one, that's the second result, and now hopefully it should finish now. Okay, and we can see how fast it was by right-hand clicking on results here, and you can see it's running in seconds, 34 seconds. So let's have a look and see my results and see if everything was connected. Okay, and we can deform the shape like that. I can make the shape a little bit more like this. Let's spin it around. Let's keep it like this and see what happens. That looks okay. And so I'm going through all the different modes to see if anything flies off. Oh, can you see here? That plate is not connected. So we need to do that one as well. So let's pick that one, next one. Let's keep going through the process. Okay, yes. Ah, there we go again. Can you see here? These plates are not connected. So, okay, that's fine. So I'll go back. Let's do these first. Go to my connections and let's do a manual connection. We can do an edge surface contact. So I'm going to pick this one here. If I say find connections, it can't find it. So let's make that gap bigger. There you go. That's done it. Oh, I forgot. I should have done the other one as well. So we'll go and do that one again and pick that edge. Make the gap bigger. There we go. That's it. And then the last one was, no, was it this one? I think it was this one here. You can find out if I right-hand click on that one and say right-hand click. See, it hasn't got any connection at the bottom. So that's one way of doing it. So let's go and create a connection again. We'll do a group connect, pick that one and pick the plate underneath. Find connections. It didn't find it because I forgot to change the gap. And there you go, it's created the contact. So this is a very quick way to check, and this method can be applied to all your other tools you're using, Inventor and Nastran, do a modal analysis. So I think I have done everything here, which is connected, and we'll do a final check. And let's see if everything is connected. Okay, just so if you have any questions, anybody, while I'm doing this, please sort of mention them in the questions for me to answer them afterwards. Okay, so let's have a look. And okay, that's fine. That's fine. So I'm going through it pretty quickly. What we are looking for is the color and see if there's any red appearing. There we go. So I think we have mission accomplished. Okay, so that was the first example. Now let's have a look at another example, which is also a very thin structure. Okay. Now you will see here a drum which is made out of a very thin structure. And it's very large and very thin. So we have, can you see here? I've even got the barcode plate in there from, I could include that in the FEA, but a good thing to do here is, if I click here, it's very, very easy in SimSolid to go and pick small objects which are not very important. So you can flick through these. Okay, I'll keep these. So I'm going to suppress that one. I don't think that plate is going to be anything significant for my analysis. So we'll go and suppress that. So this is how you can suppress. So you don't have to clean the geometry from inside Inventor or any CAD software you're using. Bring it into SimSolid. Use this tool to very quickly pick objects or components that you do not want to include in your analysis. So I'm happy with that. So what we're going to do here, let's do the first thing first. We go into my material properties and assign steel to everything. Okay, steel's been assigned, and we will do the same thing now. Because I'm, okay, let's have a look here. Let's do the connections. Going to here, 1 and 1, thin structures, we'll keep it to high here for a moment. And let's press OK, and then it will give me an indication, again, like the other example, is whether anything was not disconnected. Let's see what happens and what it comes up with. So this model, even though it doesn't have that many components in it, it is pretty complex because there's a lot of folded plates in there. Okay, 8 disconnected groups. Let's have a look. It's the shaft. Okay, okay, and okay. The reason why this is happening is if I change the view to something you can see here straight away, there are gaps. That's why. So what's the best way to do this? Well, I'm going to do something different here. I'm not going to go and create a new connection or a contact with a higher value. I'm going to use some welds here. So let's go and create some welds. Here, let's make the weld size 5. Let's do a group weld. And let's pick this piece, this piece, this piece. And then I'm going to go to the other side. For example, 5, find the welds. If I press OK, there you see it creates the welds. So what I'm going to do here is let's repeat that one for the front end here. Let's do a group weld again, but this time I'll have a bigger weld. Let's say 10 on this member here, this one, and finally this one here. And then, we're going to put a weld here between this plate as well. So we can do that by an edge. Oops, I keep forgetting, you need to do the same thing on the other side. Weld from line. So hopefully we have created the connections using the weld as an option, not the actual contacts. And let's check if everything is connected. Okay, the assembly has no disconnected group of parts, so everything looks okay. So we'll carry on. And we can now if I want to put a constraint, for example, on half of my shape here, then I would have to go and create a split face. But one of the good things about SimSolid is we can create constraints on certain faces without creating any split faces. So watch me here. Let's have a create view like that. I'm going to zoom into this side here. I'm going to now create, let's do a structural linear analysis. This one here. Click on constraints, and we have something called spot here. So I'm going to click on the spot, create a new spot, and then we define a region like that. I'm going to go and put it somewhere like that, okay, and say okay. There you go. It's created the. That's where it'll create the constraints. But I need to do the same thing on the other side. Okay. There you go. So it's constrained only the bottom half of the cylinder. So now we're going to put a load on the other side. There you go. So we're going to put the load on the opposite side on this part here. So we'll do a bearing load, pick the top surface, and 100,000, and we'll cover the whole area of the top half, 180, and I press apply. So I think we have everything done. So it's a pretty complex detailed model, so I'm happy with this. So let's go ahead and press run again. So you can see here again, it'll run through three different analyses. Okay, so let's see what happens. Again, you would have to simplify this, run this using simple models like surface models and beams, which is also time consuming. And there you go, and the result has been achieved. So let's look at this. Let me hide my load and boundary conditions. And let's have a look at displacements. Okay, that looks okay. Oh, we have a slight problem. There is, so this was a single component, but it was like a folded sheet. So you would have to fill the gap and make it into one, which can be very tedious. But one of the strengths of SimSolid is we can create a contact even though it's a single part. So I'm going to connect that together now using a contact, not necessarily a weld. So let's try that one. You would have to clean this in the CAD software if you didn't want this, which means it requires time. And so I'm going to go in here. I'm going to pick that component, and then it'll give you a warning. Do you want to create a contact between its own part? You say yes. A gap of 1 millimeter, and there you go. See, this is almost impossible inside Inventor and Nastran. You cannot create a contact between a single component. The contacts only apply to assemblies. In here, we can apply a contact on a single component like this one. So now I think we are okay, and we go and press run again. Okay, so that was quick. So let's have a look at displacement, and let's see, now that looks okay. Let's have a look at some stress results, and we have values of 40. Where is that? That is on the welds. You can see here. So what I'm going to do here is I'm going to back and hide the welds for a moment. Down. Not that one. Where are the welds? Welds, where? I'm looking the wrong one, that's why. Just a moment, there we go. Looking the wrong place, hide all, and then I can then look at the results again. And now we see the stress in the actual geometry itself. One thing I like about this software here is you can actually look at weld stresses and weld forces. So I'm going to go here and bring back the welds, look at results, back again, and then down here, can you see here? We can look at connections, seam welds. So these are all the forces on the welds. Or you can do this. Let's look at seam welds. I'm gone. Where's it gone? That's not what I wanted. I wanted this one. There you go. So that's that one there. You can look at the forces, contact moments on the welds, and then you can also look at force magnitude per length along the weld. You can do this type of thing. So it gives you a lot of information about the weld forces if you are interested in that type of information. So I hope that's given you a quick overview of how SimSolid handles welds, for example. So let's have a look at the final example. And this example, again, is a very large structure, as you can see here. Let's have a look at assembly. You also have 351 components comprised of frames and bolted connections. So let me show you here. It's probably easy if I do that. There's the bolted connections. You couldn't do this with beam analysis because you've got these stiffening plates also in the structure. So you would have to model this as either solid elements or shell elements, which can take a fair amount of time to set up and run. So I'm going to basically show you how to combine welded connections with bolted connections. So first of all, let's have a look at the assembly and the materials. Apply steel to everything. Now, when we do connections, we basically create the welds first, then we create the connections. So I'm going to hide. So I'm going to connect the columns first. So let's pick that one, that assembly, and that assembly, excuse me, press up. So I'm going to isolate everything else. So let's create the welds on here. So connections. So let's create the 25, that's not, I think 10 mils fine, group welds. Let's draw a window around everything. And this is how fast and how quick you can create welded connections. Now let's have a look in here. And what it's done there is created a weld along that small edge. I don't want that one. So what we can do here is we can increase that minimum length. That looks okay. And you can see how it creates welds along, and how many welds. It's created hundreds and thousands of welds already on the whole structure. And then if I reverse the selection, let's do the same thing here. So let's do the same thing. And let's draw a group weld, 25 mil, same one. Okay. Find the welds and see how quick that was. Trying to create welds inside Inventor, for example, using weldment assemblies can take a long, long time. Okay, it's doing something. I always get worried when it takes a bit longer. Okay, so let's see how many welds it's created just to show you what has happened. So connections, seam welds. Almost 1300 welds is created very, very quickly. Okay, so let's go back up here again. So now we can create connections between the objects. So show all. So here, this is the clever part here. I'm going to connect unwelded parts only. So wherever there's a weld in the geometry, it will ignore that and create contacts everywhere else. Okay, so that has created the connections. Let's have a look. Here, not that one. There you go. Regular connections is bonded. So let's have a look at the first one, that one there. These are the plates which are bolted. So I'm going to change the connections from bonded to separation, because these plates will be held using bolted connection with preloads. So that's very easy. Right hand click, edit default connections. We can have separating. You can specify a friction. We'll leave it as 0.1. Now you can see that should go green. That's it. There we go. It's gone green. Okay. So the next thing we can do here is we can actually apply preloads on all the bolts in there. So the quickest way we can do this, let me show you one first. In this one, And let's pick spin around. There, can you see it? You can apply bolt preloads by picking a nut. You can specify a pitch, and then you can specify a torque or whatever, but that's going to be a lot of work if I'm going to start going and picking every single bolt and nut. So let's cancel that. And in the software SimSolid, you can go to the assembly mode and you can right-hand click here and say, show me all the nuts. But I don't want to see the welds, so let's go and hide the welds as well. So hide all. So the only thing you see there is every single nut we have in here. So I'm going to draw a window around everything. Down here, nut. Okay. Right, every single, so we're going to put a 0.1 mil. You have a choice. You can specify the number of turns. When it touches a plate, define pre-torque, pre-stressing, or axials. You can specify a torque, just like Nastran, or a axial force. We'll just go in here. Oh, sorry. And can you see what happened there? It's put a twist on every single nut in here. So if I show all, and we're going to press run. And now remember, when I press run, I always forget to do that. It's a separate contact, you know that. So I'm going to run it live just to show you how fast it is. So I need to set up and include separating contact. And let's press run. So now we have a model, a large model. Did I press run? Yes, I did. We have a model with lots of welded connections, over 1,000. We have bolted connections with bolt loads, and we have about 8 separation contacts. Whoopsie daisies. I know. Why do you think it's failed? Because it's me being silly. I have forgot to restrain. The whole thing can move. So let's go and do that. That was intentional part of the presentation, guys, just to show you it's not foolproof. So now we do it again. So it goes through 1 pass, 2 pass, 3 pass, and we should be able to look at reaction forces, and we should be able to look at every single bolt, axial forces, and shear forces. I hope it is giving you an appreciation of how simple it looks. That's the whole reason why I'm doing it live, so you can see it. So now it's looking at the nonlinear contact behavior, and I'm guessing it'll probably take just over a minute. Okay, that's it. Let's have a quick look, see what sort of results we have got. Okay, let's look at the view 5. Okay, upside down. There you go. So we have the displacement results on here. And we can also look at reaction forces. The one thing I like about SimSolid is that you can, even though you created one constraint, you can have the ability to look at individual faces per constraint, or you can highlight all 3 faces to give you the total value here. And one of the best parts is this. You can have a Excel table of every single bolt in the model with all the axial force and shear forces on here. So if I click on that one, you can click on the magnifying glass down here, and it tells you where the bolt is in the model, and you can flick through all these. Pick that one there, and you can see it. So you can export this into Excel spreadsheet to actually have to interrogate your results. I hope this has given you some sort of appreciation of how fast the SimSolid can work. Then everybody may have a question about this. If it doesn't use a mesh, how the hell do we know the results are accurate? It's a question I get asked all the time. So I thought it might be useful to go through some examples. So this is a very simple document. There is the link to the theoretical example. And we've compared that example with SimSolid, and you can see the result is almost as the same as the hand calculations. And then I'm not sure if anybody here is familiar with independent body called NAFEMS. It's a body which is worldwide. It has a lot of software partners like MSC, ANSYS are all members, and they create standard tests. And I've chosen 3 of them. And if you let's pick the first one. So this is a test created to test the accuracy of the software. So this is one, so we need to target that result there. And in SimSolid, we got exactly the same result. So this is also showing you how accurate results are. The next example is a skew plate. And that result again is 2.2% difference. You can try these yourself. And then the final one is some sort of pressure vessel type example. And I've tried in 2 different models, as a full model or as a quarter of a model. And in both cases, you can see the results are accurate. So the software is accurate. We have compared it against NAFEMS report. There is a document in the handouts, which you can also, there it is, download. It's a document which compares results against hand calculations, compares through some sort of test data. And we also have more information. This was again by NAFEMS. They have created a document. You can compare results. There's the link. And here they are comparing the results against traditional softwares like ANSYS to see how accurate the SimSolid software is. And also, this is done by an independent author who uses SolidWorks, for example, and he created a document to compare SimSolid against SolidWorks results. So you have ample, these will be recorded, you'll be sent this information, so you can download it from there. But you also have this information here, which is very vast to show you the accuracy of the software. So hopefully that is towards the end of our presentation. So the question is, I hope you liked what you saw. I hope that the SimSolid can be of benefit to your company in addition to what you're already using. So and there is my contact details. If you would like any further information, you could get in touch with your local representative in the Nordics, the UK, and the States. If you are having trouble trying to get hold of your contacts, there are my email and my contact information. And I'm simply going to hang around for the next couple of minutes, 10 minutes or so, for any questions you may have. And I'm just going to whiz through some of the questions. Okay, I am using a laptop, guys. So it is, the software is not dependent on how big a machine you're using. I don't know how it does it, but it's very fast. If you have a slow machine, it will still be running very fast. Another question is the software a single user license? No, it's not. It's a multi-user license, so any person can use it in the company at one time. So I'm going to hang around for any more questions anybody's got. If you would like to ask questions individually, please get in touch and we can go through it on a case by case. What we are offering, if this is something you're interested in, we can go through, set up your models, and then you can compare how fast or how slow it is compared to your current tools, whether using Inventor, Nastran, or ANSYS. And if you like what you see, then we will make a trial version available where you can try it and run it for yourself. And one of the things you'll notice, SimSolid is very, very easy to use. If you have been trained and on FEA using Nastran Inventor, then you will need very minimal training inside SimSolid. I have a question here. Can you export weld loads as well? I am sure. Let me just check very quickly. The answer is no, Sven, at the moment. Okay, so I have another question here. Does the software handle rigid body motion transit analysis? It doesn't do rigid body motion where you can have the object moving, but you can do linear dynamic analysis where you can do vibration frequencies. So I'm afraid it doesn't do rigid body motion, but there are other tools within Altair which may do that. Okay, well, I'd like to thank everybody for their time for this afternoon or morning, and feel free to get in touch if you have any further questions. And thank you very much, guys, for your time again. Bye for now.